Yeah, there was a problem. Alright, so we are doing 9.5, which is just a continuation of 9.4. Except instead of having third power, now we have fourth power. I know. Correct. So once we reach degree of 4 or higher on a polynomial, that synthetic division step that we do in the beginning, we have to do more times. Because our goal is to get to a quadratic. So I have to keep doing synthetic division over and over and over until my quotient is a quadratic function that we can either factor or synthetic division. Okay? One of the two. So I've got a beautiful fourth degree polynomial. Go ahead and plug that into your graphing utility and graph that polynomial. We've been rocking chapter 9 for a while, dude. Since before that. Yeah, we took a quiz on it. So go ahead and graph that fourth power polynomial. X to the fourth minus 6x squared minus 8x plus 24. Where does it look like?
So what do you do?
Graph.
That's it?
Yep. Just graph.
It went away.
It's only on a second, right? It's just on that one point. At 2. Okay, well let's see if maybe we just don't see the other roots. We'll zoom out. Is there anything else? No? I'll zoom out again. See the button that says zoom? And then it says zoom out? No. And then press enter. It's asking where you want the center to zoom. Does it look like it's coming back down at all? Not anytime soon, right? So 2 is the only part where it's intersecting our x-axis. Okay, well, alright, let me zoom back in. Oopsies. Graph. Okay, so we just got that one point. Alright, well, let's go from there then. Let's start with a 2. Alright. So 2. So we need to do synthetic division with 2. What numbers are going to go next to? 1. I'm missing 1.
0.
Where? Before the negative 6. Alright, there's several side conversations going on that I don't know whether they're relevant or not, but I'm having a hard time hearing the students that are talking to me. So the reason we need that placeholder 0 is what exponent am I missing in that polynomial? I'm missing x to the third. So I have to have that placeholder 0 to account for the missing x to the third. Okay? So I've got 4, 3, 2, 1, 0 on my power, so now I can do my synthetic division. Okay, walk me through that again.
Bring the 1 down.
Okay.
2 times 1 is 2. 2 times 2 is 4. Negative 6 plus 4 is negative 2. Negative 2 times 2 is 2 times negative. 2 times negative 12 is 4.
Okay. So, is 2 a 0?
Yes.
Yeah. Alright. We saw the intercept. We had 2 as a 0. What is this resulting quotient? Is it a quadratic? I divided x to the 4th. X cubed, right? So I have x to the third plus 2x squared minus 2x minus 12. Okay, can I factor that? Not yet.
Need to divide again.
By what? I don't have another intercept. Graph that. Graph the cubic. The cubic. x to the third plus 2x squared minus 2x minus 12. Let's graph that one. Well, I don't have any other intercepts here. So I don't have anything else to do synthetic division with. So I'm going to graph the new one, and I'm going to look for another intercept.
Why don't we just solve that?
We're going to graph it again. Goes through 2 again. What is it, if I do synthetic division, what do I need to have to verify that it's a 0? What do I have to have? What am I looking for when I do synthetic division? No remainder. Okay, so we could do it with any number we want as long as it gives us no remainder. So we graph this, we see that it intersects through 2 again. So let's use 2 again and see if we get a remainder of 0. So 1, 2, 4, 8, 6, 12, 0. So again, the reason that we can use 2 twice is because, see how it comes down and it touches the x-axis and then it goes back up. Okay? It touches the axis and it goes back up. We call that a multiplicity of 2. Meaning that 0 counts twice. Which is why when we graphed that cubic function, it also went through the x-axis at x equals 2. Because that 0 counts twice. And we're going to kind of come back into some fundamental theorem of algebra stuff with that information. But it's a really important fact. And I know I've mentioned it before. If I look at the leading exponent, if I look at the degree of the polynomial, that tells me how many answers I get. So with a degree of 4, how many answers should I have? 4. Sometimes they duplicate. So 2 is my answer twice. Because it touches the x-axis and then it comes back up. But then when you look at the graph, see how when we graph the cubic function, how it goes straight through. So it doesn't have that multiplicity anymore because I got rid of one of the 2's. So that multiplicity is gone, which is why the graph goes straight through. Okay? So now let's look at our new quotient. What's that new quotient? Okay? So now we have a quadratic. So because we started with a 4th power polynomial, we had to do synthetic division twice. We had to do synthetic division twice in order to get down to a quadratic. That's the goal. And now when I'm at a quadratic, I can factor and solve. And then what's my backup if I can't factor? Quadratic formula. Okay? So can I factor? Can I multiply anything to get 6 but add to 4? No. So I can't factor, so I have to use quadratic formula. Okay? So that means I'm not going to have any more rational roots. I've gone through them, and we see that. Those are my only rational roots. Okay? But also keep in mind that I don't have any other x-intercepts. So let's see what happens. So negative b plus or minus square root b squared minus 4ac over 2a. What's my b value? 4. Okay, so simplify 4 squared minus 4 minus 4 times 1 times 6. What's my discriminant end up being? B ends up being negative 8. Okay, alright, so now I need to simplify square root of negative 8?
2 square root of 2.
Close. 2i square root of 2. Because I got that negative. It's going to give me that imaginary root. So now I have 2 imaginary roots, which is why you don't see any more x-intercepts, because those last 2 solutions are imaginary. Let's graph this real quick, the x squared plus 4x plus 6. Okay? And just see how this transforms as we keep taking out roots. As we keep finding more and more roots and factoring our quadratic. So I'm going to graph that last one. The black line there is that quadratic. Where does it intersect the x-axis? Nowhere.
Is the imaginary the y-axis?
Graphing complex, but that's a different thing. This is the Cartesian grid. Doesn't have no solution. It's 2 imaginary roots. No x-intercepts means it's an imaginary root. It's an imaginary solution. And we saw that mathematically when I ended up with this. I can see now that my last 2 roots are imaginary. So we simplify that radical. Simplify the radical. Divide by 2, by 2, by 2. So I get negative 2 plus or minus I root 2. Now remember, that's 2 answers. The positive and the negative. Okay? So that's 2 answers. And remember, I have a degree of 4, which means I have to have 4 answers. So I've got this one. I've got this one. I've got 2. And I've got another 2. Because that 2 counts twice. Because of the multiplicity. So the way that we describe it is we'll say 2 with a multiplicity of 2. And then we have the 2, negative 2 plus or minus I root 2. That covers all 4 solutions. But we have to identify that as zeros. We have that the 2 counts twice.
If you wrote the other answer, would that also do it?
Yeah. So our number of solutions has to match the degree of the polynomial. Sometimes those solutions duplicate. Sometimes those solutions are imaginary. But it has to be equivalent, okay? And that derives as part of our fundamental theorem of algebra, okay? Yeah.
So when we use synthetic division to like simplify, anything that we have there.
Yep.
So anything that's part of that even.
Yes, because
so like, let's say we had 2, and then the second one could only be solved like a 4.
Yeah. So once you get here to this, you can re-graph this equation, and any intercepts of our cubic is also going to be an intercept of the 4th power.
Okay.
So any of the polynomials that we get as factors,
Like let's say we had a 2 and a 4. That 2 and the 4 are kind of interchangeable in the order.
Yeah. Just like when we had yesterday with factoring some of these, like back here, we had -1, 3, and 2. It doesn't matter which one you do synthetic division with, you'll end up getting all the same factors. So again, it doesn't matter which 0 you divide with first, because it has a list of its factors, and as you factor it and break it apart, it's going to lead you to the other ones. Okay? And so once you do the first synthetic division, if you are having a hard time finding your zeros, graph it again with the quotient and see what its zeros are, and then use that for synthetic division until you get to your quadratic. Okay? So, a polynomial equation of any degree, if we count roots that are multiples that appear over and over, okay, we have those multiplicities, the number of solutions has to be equivalent to the degree of the polynomial. So if I have a degree 5, how many roots am I going to have? 5. If I have degree 12, how many roots am I going to have? 12. If I have degree 1, how many roots am I going to have? 1. Okay? Now, the other thing that's really important is this. If we have a complex root that is imaginary, they always come in conjugate pairs. Imaginary roots always come in pairs. Because what's our quadratic formula? Negative b, what? Plus and minus.
If you're going to have an I, it's going to be...
Exactly. If we're going to have an I, square root of something, there's always 2.
And there's no way that you can combine those.
Never. They're never going to be the same thing. Hey, what's up? Okay, so imaginary roots always come in conjugate pairs, which is important to remember that that's going to count for 2 of your roots. And so if I have a plus bi, I have to assume I'm also going to have a minus bi, or vice versa. Where this is most important is what we're going to do as the last example in just a moment. Okay, so the fundamental theorem of algebra states that if we have a function that is a polynomial of a degree that is greater than or equal to 1, so we have a polynomial, then the equation, when we solve for it, is going to have at least one complex root. So all polynomials have roots. Complex numbers is everything. Our real numbers are complex numbers, where the imaginary part is just 0. And then we have our imaginary numbers, and the imaginaries always come in conjugate pairs. So that statement leads into that idea of the number of roots has to equal the degree. They have to be the same. And then roots counted according to their multiplicity. If we have a root that shows up more than once, then it counts towards that total. So this question is basically asking us to go into reverse, but we have to keep in mind that fundamental theorem and that conjugate nature of imaginary roots. Find a 4th degree polynomial, which means I have to have how many roots? 4. I need to have 4 roots. 4 roots. Or solutions. Or zeros. Or not necessarily x-intercepts, because they might be imaginary. Oopsies, go back. Not done with you. Alright? 4 roots, solutions, or zeros. Okay? So, the function has real coefficients. Don't worry too much about that. That just says, hey, our math is going to be easier. A leading coefficient of 1, again, our math is going to be easier. If we had a leading coefficient that wasn't 1, then there'd be some extra steps involved to find that. What we need to focus on is it has 1, 4, and I as zeros. How many zeros is that? 3. How many am I supposed to have? 4. So I'm missing 1. Not a multiplicity. In theory, that is a possibility, but it's not going to be the case because they would tell us the I needs to be plus and minus. If there was a multiplicity, they would tell us. They would say 1, which has a multiplicity of 2. They would tell us if there's a multiplicity. So you have to think back and remember that imaginary roots come in conjugate pairs. They only gave us one of them. So we have to assume that negative I is also a root because that's its conjugate pair. So I have 4 zeros. I have 1, I have 4, I have I, and I have negative I. Now yesterday we reviewed going back and forth between roots and factors. Because I need to take those roots and I need to write a polynomial. So how do I work backwards and take a root and write a factor? That would give me that solution. If I have x equals 1, what factor would give me that solution. Close. X minus 1. If I have the equation x minus 1 equals 0, that gives me the solution where 1. So if we work backwards, and all we're doing is we're moving everything to the same side of the equation to set it equal to 0. We set each of these equal to 0. And that's going to give us our factors. X minus 1, x minus 4, x minus I, and x plus I. So we take our roots, or our zeros, we work backwards, and we find our factors. Take our roots, we work backwards, we find our factors. So f of x, the function that I'm trying to find, has factors of x minus 1, x minus 4, x minus I, and x plus I. Now all we have to do is just multiply it all back together. That's it. Now the trick is, you'll want to do it in a very specific order, just to make your life easier. You don't have to do it in this order, but if you want your life to be easier, you're going to do it in this order. Do the imaginary ones first. Because recall at the end of chapter 8, when we talked about imaginary numbers, we first introduced those in conjugates and conjugate pairs. The product of conjugate pairs is always a real number, or a real. We take two conjugate factors and we multiply them together. I will get a real factor, a real expression with no more conjugate values. Bro, I ain't even done.
I know, I'm just making sure.
So we're going to multiply these first. Just distributive property. What's x times x? X times I, ix. Negative I times x. And then negative I times I is negative I squared. So then we simplify. What is ix minus ix? 0. That cancels out. What's I squared? Negative 1. And then when we have that subtraction, it turns it into a plus 1. So I have x squared plus 1. So the product of x minus I and x plus I gives me x squared plus 1. It's real now. So we got rid of those imaginary parts, which makes it just uglier and more complicated. So then we can continue factoring with it, or distributing with the other two. X squared minus 4x minus x plus 4. Combine like terms. And then we just need to distribute with the last two to get one polynomial. So we just multiply it again one more time. You could, but I'd have to get rid of either the 1 or the 4. Because conjugate pairs always come in pairs. So if I have one, I've got another. Okay? So x squared times x squared, x to the 4th, plus x squared, minus 5x to the 3rd, minus 5x, plus 4x squared, plus 4, and then we just combine all like terms together. Once we combine like terms, it will be. So I'm starting with x to the 4th, then I go to my next lowest power, which is 3. I'm going to put that next. There's no other like terms, so I write 5x to the 3rd. Then I go down to my second power. I have x squared plus 4x squared to get another 5, and then x squared. Then I go down to my x to the 1st. There's only that one term, negative 5x. And then I go to my constant. There's only that one term. There's f of x, standard form. Yeah, it is. That's so, a 4th degree polynomial that has 4 roots, multiplied all together. Now, that conjugate pair was a little bit nice. I'm going to show you another conjugate pair that's less nice. I mean, I don't have to do the example, but you're going to see it later.
Okay.
So, I gave you I as one of the roots. So, let's talk about a less nice conjugate pair. Okay? So, if I have a root, let's say x, instead of just equaling something nice like I, let's say it equals 2 minus I. What's the conjugate pair for 2 minus I? 2 plus I. Okay, just change that sign in the middle. So there's my zeros. Let's work backwards to get the factors. So I'm going to subtract 2 and I'm going to add I. X minus 2 plus I. And then I'm going to subtract 2 and subtract I. X minus 2 minus I. So there's my two factors, x minus 2 plus I, x minus 2 minus I. A little bit longer, but it's still distributive property, and it will still give us a real polynomial when we distribute and multiply. X times x times negative 2, x times negative I. Then we move on to the negative 2, and we keep distributing. Negative 2x, positive 4, positive 2i. And then we do the last set. This is where stuff will start to cancel. Positive ix, negative 2i, and negative I squared. Negative ix and positive ix. Those cancel. 2i and negative 2i. Those cancel. And what's negative I squared end up equaling? So negative 1, which is positive 1. And then we just combine like terms. X squared minus 4x plus 5. And there's that resulting real polynomial from those two conjugate pairs. Okay, same process, just a little longer. Concerns, queries,